In an earlier video, I gave you a good starting working definition for chemistry, which is the study of matter and the changes that matter undergoes. And I gave you a not so good definition of matter at that point. I said matter is anything that has mass and occupies space, which doesn't really help you sink your teeth into the idea of exactly what is it. And you cannot understand exactly what matter is without turning your attention to the atomic theory. Atoms make up elements. All elements are comprised of atoms. And elements, in turn, are the building blocks of matter. And we just looked at how the periodic table organizes all the elements that we've been able to observe and characterize. So in order to understand matter, which is made up of elements, we have to take a look at the atoms which comprise elements. So we're going to first, in our discussion of the development of the atomic theory, look at John Dalton's atomic theory, an English school teacher who was fascinated with science as his true passion and hobby. And based on a number of experiments that he conducted, he was able to publish around 1805 his atomic theory, which is the foundation for our understanding of what atoms are. Notice this theory was published around 1805, and I'm always fascinated with the fact that it's not that long ago and how much we've learned in a little over 200 years. So here are the points of Dalton's atomic theory that you're responsible for knowing. All matter is made of tiny particles, which Dalton called atoms, in honor of a Greek philosopher that first suggested over 2,000 years ago that this might be the case, but did not have the experimental data to validate his ideas. So in honor of Democritus, Dalton named these tiny particles that make up matter atoms. His second statement is that atoms of a given element, all atoms of a given element are the same, and they differ from atoms of other elements. Atoms of a given element are the same and different from atoms of other elements. His third point, atoms of two or more different elements combine in fixed whole number ratios to form compounds. An example is water, H2O. We have two atoms of hydrogen combined, chemically bonded to one atom of oxygen in a fixed whole number ratio, always that ratio for the compound water. So from this statement, we get our law of constant composition, that compounds have fixed, definite combinations of two or more different atoms. The last point of Dalton's atomic theory is that atoms are neither created nor destroyed in chemical reactions. They're merely rearranged or separated or combined in new and different ways. So from this, we understand the law of conservation of mass, that we're not creating mass or destroying mass in chemical reactions, just merely rearranging, reassembling, or separating. And in this example, I'm giving you the chemical reaction for the formation of water from its elements, hydrogen and oxygen, pointing out that we discussed how hydrogen and oxygen are both diatomic elements in nature, and they will combine together in a definite fixed whole number ratio to form the compound water. And then I've used the coefficients 2 in order to satisfy this law of conservation of mass and account for all of the atoms that are involved in this reaction. So I see that there's a total of 4 hydrogen atoms on the reactant side, 2 oxygen atoms, and our products show a total of 4 hydrogen atoms and 2 oxygen atoms. So we have not created or destroyed atoms, just simply rearranged them and combined them in new ways in this reaction to form water. So John Dalton is our starting point for our modern atomic theory, but note, Dalton was not aware of the existence of particles of matter any smaller than the atom. He thought that the atom was indivisible and nothing smaller than the atom existed. Well, scientists came to discover over the period of time that passed around the late 1800s that that's not the case, that there are actually subatomic particles, smaller particles of matter that are found within the atom. And they were discovered in this order. The electron was discovered first, and here's how we symbolize it with a lowercase e and a superscript negative charge to it, because the electron is a negatively charged particle. The next subatomic particle that was discovered was the proton, symbolized with a lowercase p or sometimes with a p and a superscript positive sign, because the proton is a positively charged particle. The last particle to be discovered was the neutron, and it is symbolized with a lowercase n or an n raised to the 0 power because it has no electrical charge. It is a neutral particle. And since we're speaking about charges here, it's important at this point to introduce you to the idea of electrostatic attraction and electrostatic repulsion. These are two important concepts that we'll be using throughout this semester as we discuss and learn more about chemistry. So, electrostatic attraction. Opposite charges attract. So an electron, which is negatively charged, is going to be attracted to a proton, which is positively charged. Electrostatic attraction, a powerful force of attraction that operates and explains the structure of matter and the behavior of matter. There is also electrostatic repulsion forces. And in this instance, repulsion operates between like charges. So like charges repel each other. A negatively charged electron will repel away from another negatively charged electron. Positively charged protons experience repulsion with other positively charged protons. So like charge repels, electrostatic repulsion. Opposite charges attract, electrostatic attraction. With these ideas in mind, scientists then asked, well, how are these subatomic particles that we know are present in the atom actually arranged? The first individual to postulate that was Thomson, J.J. Thomson, and his model was known as the Plum pudding model. And a point here to mention, the neutron had not yet been discovered. So Thomson's model was just working with electrons and protons because neutron subatomic particles had not yet been discovered. So in Thomson's Plum pudding model, there was the sea of positive charge created by the protons, and the electrons were then just embedded in it like plums in a pudding. Thomson's model was investigated by a scientist named Rutherford. And Rutherford was the one to discover and propose the nuclear model of the atom. And his model was based on a very powerful and significant experiment known as Rutherford's gold foil experiment. You'll see a description of this experiment in your text, figure 4.7. You should be familiar with the major themes of this experiment, very simple but very elegant in terms of what we learned from it. What Rutherford did was propel or shoot positively charged alpha particles. Now, this is not something you're familiar with yet, but in our next chapter, you will become more acquainted with it. Alpha particles are massive radioactive particles, and they have a positive charge. That's important based on what we just talked about in terms of electrostatic attraction and repulsion. Alpha particles, these massive radioactive particles with a positive charge. They were propelled, shot at thin gold foil, like aluminum foil, very thin, but made out of gold instead of aluminum. So the experiment in terms of Rutherford's eyes was sort of like shooting cannonballs, alpha particles, at tissue paper. And what would you expect if you shot a cannonball at tissue paper? You would expect that the cannonball would just blast through, pass right through the tissue paper. And in fact, that's what was observed. Most of the alpha particles passed right through the gold foil, but some were deflected away from the gold foil at angles, and some seemed to hit the gold foil and almost bounce right back in the opposite direction away from it. Wow, if you shot a cannonball at tissue paper and it bounced right back at you, what's in the tissue paper to account for that observation? These are the conclusions that Rutherford came to as a result of this experimental data and observations. His first conclusion: most of the volume of an atom is empty space, because most of the alpha particles just passed right through the gold foil and never encountered anything. But, second proposal, there must be a small, very dense core within the atom, because only something very dense could change the direction of movement, momentum of alpha particles, which are massive particles themselves, from an atomic perspective, and send them backwards. So there is a small, very dense core within the atom called the nucleus. So Rutherford coined this idea, nucleus, where most of the atom's mass is located. So most of the mass in a very small volume within the atom is going to give you a very high density for the nucleus. Third point, the nucleus must be positively charged, and therefore that's where the protons are located. How do we know that the nucleus is positively charged? Because alpha particles are positively charged. And what sort of force was experienced when alpha particles pass close to the nucleus? So coming over here, if the nucleus is positively charged, because that's where the protons are, and the alpha particles that you're shooting at the nucleus, and I'm using the Greek symbol for the letter alpha, first letter of the Greek alphabet. If the alpha particles are positively charged, then as they approach the nucleus and if they come in direct contact with it, we know that light charge repels, electrostatic repulsion. So if that alpha particle made direct contact with the nucleus, electrostatic repulsion would send that alpha particle almost 180 degrees backward in terms of its direction and momentum because of that repulsion. So very important conclusions made from Rutherford's gold foil experiment that led us to the understanding that all atoms contain a nucleus within them where the protons are located, and when the neutrons were discovered, they are also located in the nucleus as well. From this point, we can move to a summary now of what we know about subatomic particles and how they are arranged within an atom. So we've discussed the three subatomic particles: protons, neutrons, and electrons. We've discussed how we can symbolize them, their relative charges, right? So not the actual magnitude of electrical charge, but how they are relative to each other. A proton is given a +1 charge and an electron a -1 charge, meaning that they have the same magnitude of electrical charge, very tiny amount of electrical charge, but equal in magnitude to each other, hence the 1 and 1, but opposite in charge. Hence the positive 1 for the proton. Electron has the opposite but equal amount of electrical charge, hence the negative 1. In terms of the mass of these particles, and notice we know that atoms are very tiny, subatomic particles even smaller, so scientists had to introduce a whole new mass scale in order to be able to express the masses of such small particles. This scale is known as the atomic mass unit scale, or abbreviated AMU. Looking at the masses of protons and neutrons, we see they are almost identical to each other, with the neutron being just a little bit greater in mass than the proton. The electron is significantly smaller than either the proton or the neutron, with an atomic mass unit value of 0.00055. And I don't expect you to memorize that number, just to be aware that the mass of the electron is significantly smaller than that of the proton and the neutron, approximately 1/2000th the mass of protons and neutrons. The protons and neutrons are located in the nucleus, and collectively their mass in total determines most of the mass of the atom, because the electrons have such a small amount of mass relative to protons and neutrons. So protons and neutrons contained in this very small volume, the center of the atom that we call the nucleus, and the electrons are moving around outside of the nucleus. Well, if they're moving, why don't they just fly away? And the answer is electrostatic attraction. The electron is negatively charged, and electrostatic forces of attraction hold the electrons in contact with the nucleus, moving around outside of the nucleus.